Hello, everyone. My name is Naftali Cohen. I'm a VP and research lead at JP Morgan AI Research. In addition, I'm an adjunct professor at NYU Tandon School of Engineering. I will be talking today about using AI technology to understand how financial decisions are made. So at JP Morgan, I'm leading a team, and I will be talking about work that was done in my team. In particular, the main collaborators were Swijan Sood, Jean Zhang, Tucker Bolch, and Manuela Veloso. So as I mentioned, I will be talking about using AI technology, but a better title to my talk is going to be Visual Perspectives in Finance. Before I begin, I would like to say two words about my team, or about the group as a whole. The group as a whole is led by Professor Manuela Veloso. We are about 50 people. We pursue academic research in the domains of machine learning, AI, and reinforcement learning. But at the same time, we are highly business oriented towards the domain of finances. We exist for 2 or 3 years and are now about 50 people. We operate largely in the 7 domains that you can see here on the right: data and knowledge, learning from experience, reasoning and planning, safe human AI interaction, multi-agent systems, secure and private AI, and machine learning and language. So as I mentioned, the work that I will be presenting is the work that was done mainly in my team. But in addition, we are highly collaborative, extremely highly, with external people, external academic, and external units. Many of what I will be presenting was done in a joint effort with students at Columbia University, the Data Science Institute. In particular, I will be talking about the work that was done during 2019. We are actively working with Columbia University on various projects, and ongoing efforts are marked in red. If you want to talk about it later, you are welcome to contact me. So the main question I will be pursuing in my talk is the following. In the financial market, people are making impactful decisions. For example, selling a property, providing a loan, or maybe investing in the stock market. Can we quantify and model the decision-making process? And in particular, the main topic I will be discussing is that humans rely on visualizations for decision-making. Let me reiterate this point. In the image in front of you, you can see a trader about to make a trade or about to make a financial decision. He is, of course, he has like a multi-screen environment, and he might be professional, knows a lot about his domain, and he is about to make a decision, and to his aides, you can see that there is a lot of information in front of him. Most of the information is in the form of tables, or if you like, raw data, numerical data. But as you can see, about 50% of the screen space is occupied by visualizations. So the main argument that we'll be pursuing is that when we are making decisions, we are being aided by visualizations, and that's part of the decision-making process. Can we quantify, or can we use can we quantify how much visualizations contribute to the decision-making process? That basically is the topic, if you like. But when it comes to visualizations, in particular in the physical space and decision-making, we have to have the ability to collect information from the physical space. So in our team, we have a lab. In that lab, we have attention tracking devices that allows us to extract and quantify information, attention information that's happening in the physical space. On the left, you can see me actually watching the news. It was back in 2019, and as I watch the news, you can see how my attention is distributed over the screen. So when someone is talking, I'm focusing on his face, in particular the lips, and then from some time I get bored, so I get to I go and read the title, and then there's something interesting here. So my attention is basically following what is exciting on the screen. On the right, you can see me again watching the an NBA game, and then you can see that I basically follow the attention. Sometimes when a player is shooting towards the basket, you can see that my attention goes very fast towards the basket even before the ball is hitting the basket. So that's human nature, if you like. But you need to be able to extract that information from the physical space. So you need to have a device for that. What are the implications? For example, here now you can see a trader using a Bloomberg terminal, watching, and doing his thing on the screen, and then we can extract that information. For example, we can use some ML technique to cluster his attention as he moves from one regime to another, and then in the end he will be making a decision, and we can ask how did he come to make that decision. So whether the decision depends on previous sequential activity. So we need to have the ability to extract, organize the data, and then relate the decision to a previous sequential activities. So decision-making in the physical space is, of course, very complex question. Can we quantify it? So in order to quantify it, we came up with some sort of an isolated decision setting, if you like. You can call it decision making in the 1D space, in the horizontal space. So we asked people in our department what comes next, and then we showed them a presentation in which you, for example, see some bunch of numbers, if you like, horizontally, and then the question is what comes next. So you can see numbers that go that are basically our increments by 1, so 0, 1, 2, 3, 4, 5, 6, 7, 7, 8, 9. What comes next is, of course, 10. But notice that in order to choose the right answer, you have to glance, or you have to look horizontally. So it's like a 1D decision-making process, and you must observe that in a sequential manner. So that's like the most simplified decision-making scenarios that you can imagine. So we ask people, various questions to kind of using the eye tracking devices to try and measure the decision-making process. Here in that example, it's like the 1D scenario. So that, for example, you can see the word imagination. But in order to figure out that the next inline letter is N, you have to again observe sequentially from left to right in the horizontal space. So here you can see people taking the test and making decisions. Each time they were confronted by different patterns that they had to recover. And then you can see how the decision making is happening. So that's here you can see, for example, people trying to figure out the Fibonacci sequence. Here people try to figure out the next word in a song and uncovering some cyclic patterns. And then, of course, once people are being experimented, you can extract that information and as a time series and try to quantify, try to understand how people are making the decision and whether there are variability between people. So I won't tell you much about the conclusion of that particular project, but it was done in 2019 in collaboration with Jinmin Lee. Later on, we extended that effort into the 2D space. So here we asked people to solve the Sudoku. Here you can see, one person trying to solve it. It's actually purely in Python. And here the motivation is the following. Let's extend the decision-making process from the 1D into the 2D domain. Sudoku is very nice because it's gridded, so it's nice to analyze. Here the motivation was to extend the previous work, but also to try to differentiate between experienced people, professionals, and novice. So the idea is that novice people or people with no experience in Sudoku will solve it or will manage to figure out the solution in somewhat uniform ways. They will have no strategy. Whereas experienced people will have some strategy. So they will solve it column-wise, row-wise, or regime-wise. So in that way, you can differentiate between how people make decisions in the 2D gridded space. That is a joint work that was done with 5 different students, again, from Columbia University. And in particular, what they did is that they extracted the information using attention tracking devices, and they came up with some feature processes, or they extracted a few meaningful features that allowed them to differentiate between professionals and beginners. And here you can see the model and prediction results of the models that they came up with. Another project that basically in the same domain. So when I was talking about extracting attention from the physical space, sometimes it gets complex as the physical place is also complex. So for example, here you can see a trader in the trading floor, but he's observing many screens. In that particular example, 12 screens. So the problem with attention tracking devices that sometimes they are tied to one particular screen. So in that particular project, we wanted to expand that capability to a multi-screen environment. And in addition, there was one problem is that eye tracking devices is very expensive, tend to be very expensive. So so that particular team, again from Columbia University Data Science Institute, use webcam in order to separate each screen into 9 different regimes. And they were able to show that it's just using a webcam, it's possible using deep learning techniques to differentiate between the 9 different regimes or to solve the 9-class classification problem per screen. So here you can see that just by observing, using webcam, observing people's face, you can tell which regime they're looking at on per screen after you kind of split each screen to 9 different regimes. So that was very successful. Okay, so I talked a lot about extracting information from the physical space. Now let's talk more particular or more rigorously about using visualizations to make decisions. So we invested a lot of effort in the domain, and let me tell you briefly about a few published work, peer-reviewed work that we conducted on that domain. So as I mentioned before, decisions are made while observing images. So let's actually try to quantify it. So when it comes to the trading work, of course, there are various trade algorithms. Some are based on human intuition, some are based on maybe technical approaches or far more complex algorithms. In that particular project, we are not trying to argue that we can predict the market by any means, but we are trying to figure out whether we can uncover the way that people trade. In particular, we argue that people are using or their decision-making is augmented by visualization. Can we actually use that and only that to make trade decisions? So here you can see an example. So In the following figure, you can see the Apple stock from 2018. That's daily data on the x-axis month, and US dollars on the y-axis. And on the solid black line is just showing you the close value, again, daily data. And then you can take a portion of that data, and you can look at more informative information. For example, the open, high, low, close data in a candlestick form. And then you can basically pick portions of the data, make an image out of that. And then you can collect many images, if you like, from the data. And then you can tag those images according to what you want. So in that particular example, we tagged these images according to buy or not buy a signal that we got from some algorithm. And then the question was, now, if the only thing that the model is seeing is these images, can you use that to make decision? Or what's the value of making trade decision based on visualizations alone? So saying it again, we took time series data. We made from the data, we made images. And then we tried to solve the classification problem using images alone. So what we did, we collected many images. Each image was tagged differently. In that particular example, it was tagged according to buy, no buy classes. So for example, you can see that image was tagged as buy because you can see there is a local minima. You of course don't know what's going to happen later, but still it looks like a local minima, so we tag it as a buy. If there is a local maxima, or in all cases that are not tagged as buy, we define it as not buy. So you collect plenty of images like that, actually, about 10 or 50,000, according to these two classes, and then you run machine learning algorithm on the data, and you ask whether the model can differentiate or allow you to make decisions based on visualizations alone without seeing the numerical data. And what we showed in that particular study, that yes, the model, we tried actually 15 different models, that these models are able to differentiate significantly between the two different classes. And here is an example of how you can use that sort of method, test time, when you run it on out of sample examples. You can just use some rolling window on the data, and then for each point in time, you make an image. You let the model analyze that particular image and make a decision based again on the visualizations alone and not the numerical data. In a different study, we looked at learning from subjective information. Let me tell you a little bit the story about that particular one. So teams at JP Morgan analyze the data, they call it the market health, or the S&P 500 index, in a form of 5 different features. So these are the features. That's particular example for one particular week. So you represent the market health in a form of 5 different features. But for some reason, over the past 10 years or so, in their publication, they have decided to present the data to their client in a form of a spider map visualization. So we asked the question, what's the value of using the visualization as opposed to just using the numerical value when you run some algorithm on the data? So which one is better, the numerical representation or the visual representation that the professional people choose to use when it comes to learning from the data? And what we showed, and you can read it up on one of our papers if you like, is that the visualizations are better. They they contain more information. Of course, that information is subjective. There are many ways to represent data, but that's the way that the professional people at JP Morgan decided to use or to represent the data over many, many years. And we basically argue that there is value in it. And we actually showed that for classification problem, that particular visualization has an edge compared to just the numerical form of the data. And let me tell you lastly about another project that we conduct, which is now, it's a regression problem. So before I was talking about, give me one particular image. Can you tell me which class that image belongs to? So that's the classification problem. But now let's talk about value prediction or the regression problem. Can you give me an image of one particular time series? Here it's just some harmonic data. And then you have some sophisticated model, machine learning code. In that particular example, it's an autoencoder. But you want the autoencoder to spit out a different image that will tell you what's going to happen next. So again, it's not a numerical routine. It's just image to image process. You give me one image and the model is going to tell you a second image of what's going to come next. So here you can see that's, for example, the input image, and that's the output image. In blue, in light blue, you can see some overlap, some overlap regime, which means how well the model is doing in terms of replicating the data. And in light red, you can see what the model is predicting that's going to happen. So again, here you can see the input output and the evolution of the prediction. Yeah, and we tested our complex deep learning model on various data sets. One is extremely predictable, harmonic data, and mean reverting process, EKG, and financial data. And we tried various algorithms, and I won't go into the fine detail, but you can see here on the bottom, you can see how well we do on financial data. So that's the input. That's the input that the model sees. That's the ground truth. That's what we are trying to predict in our image-to-image method. And these are the 4 different algorithms that can be run on the data: random walk, numerical AE, some traditional method, ARIMA, and visual AE. And you can see that visual AE, which is our method, is able to forecast to some good degree, in particular the trend, very good. So that's a prediction, and that's a ground truth. And of course, you can make that image to image. One of the edges is that it gives you not only value predictions, but somewhat confidence interval about the prediction. But you can also trace the maximum value in each image, and then you can get extremely well-defined value prediction per image. And we compared our method using various techniques or various ways of measuring how accurate our method is, and we show that our method outperform traditional methods. If you like to read more about it, it's actually published work, so you're welcome to search it up or just contact me later on. Let me conclude. At JP Morgan AI Research, we aim at quantifying and modeling the decision-making process and focus particular attention on relating actions to previous sequential activities. The main focus is on decisions that matter and actionable data, for example, financial data. However, in practice, we take small steps and examine simplified, isolated environments, as I mentioned in the first half of my talk. We showed there is value in transforming typical trade or forecasting work to the computer vision domain. Thank you very much.